We have looked into the finite element formulation itself. We saw that it has various elements, various matrices, but I told the devil is in the detail. So at this point it's good to start with a detailed analysis on how the matrices are filled, what are there inside the matrices, which will also lead us to looking into the basis functions and mapping from a local to global basis functions, and things of that sort will come into play. So at this point it's good to go into the discussion on the formulation itself. So the first question comes is, what is going to be the choice of the basis function? Because we told we are going to expand the unknown inside each of the finite elements using certain basis functions whose properties we know clearly. So the question comes, what should be the choice of that basis function? So let's look at the entire domain. For our analysis, let's keep the domain to be a one dimensional space. We are going to define the starting point and ending point, which we call it as the boundaries, and the intermediate points are going to be discretized, in other words split into finite elements, and that's what you see here in this slide. So the starting point and ending point of the domain is fixed, so we have x0, xn, and then the intermediate points are arbitrarily broken. It need not be equally split, it can also have smaller parts and bigger parts. Irregardless of what is the size of the individual elements, we call them as finite elements, and they are defined as sigma 1, sigma 2 until sigma n. As you can see, there are totally n plus 1 points. So n plus 1 points in this linear space gives to n finite elements. So now we are going to introduce a mapping from each of these elements sigma I to a reference element, which we call as sigma ref. So what we are essentially doing is a kind of a transformation that goes from local to the global elements. So let's see this a little bit more in the slide here. So what we have got is some arbitrary number, let's say x7 and then x8, and let's say the coordinates of x7 and x8 are some arbitrary number 0.56 comma minus 0.23, and then let's say x8 is 0.59 comma minus 0.14. So it's quite cumbersome to take each of these individual points and then identify what is going to be the points, individual points that we are interested inside the domain. So what we do is we kind of forget this and we try to map any physical element to an arbitrary reference element whose point is always going to go from 0 to 1. The reason for doing this is very clear, where each of the points inside the physical element can be uniquely mapped to a reference element, and we know that this mapping is unique because each of the points will be uniquely referred here. So that's what we are going to do. So instead of worrying about the individual coordinates on these physical elements, we can directly map that physical element to a global element or a reference element, which we call it as ref. So this is called as a reference element, and this is the physical element. The mapping will give us the behavior of or the positioning of each of the points on the physical element. So that is what we are doing in this slide. So we say x minus x of k minus 1, which in this example which I have given will be x of 7, and this will be x of 8, and we are trying to map that point. So what we are doing here is we can know that each of the points inside the physical element will have a unique point in the reference element. So for example, what I have said here is when the value eta is equal to 0, I will be on the point x of k minus 1, exactly at the starting point. So if I put eta equal to 0, k of x will give me x of k minus 1. Similarly, if eta is equal to 1, what I will get is directly this x of k minus 1 and minus x of k minus 1 will get cancelled. So we will go and get the value x of k, and the superscript here gives the coordinate. This is the kth element. So this is the kth element, that is why there is a x of k here. So similarly, if we do the arithmetic and if we assume that the length of each of this element is given as delta of k, we can write the expression and get the unique value for the eta of x. So eta of x is nothing but the value of x that we are interested inside each of these elements, and these are mapped to the reference elements. So the idea of working with reference element is easier convention because we know each of these points will always vary between 0 and 1. So we do not need to worry about what is the starting point and ending point on the physical element. So while we do that, we can also introduce the basis function itself. So I said the reference element will always have the point starting 0 to 1. So let us introduce certain nodes on the interface. So what we have got here is, we have got the inside the reference element there is a left point and then the right point, and that is what we see inside the each of the individual elements. Inside each of the individual element there is a left point and there is a right point. There is a left point and the right point. So the left points are represented as the red point and the right points are represented as the yellow points, and that is exactly coming from the mapping to the reference element. So what we essentially do here is, inside each of this physical element the mapping is done to the reference element. So this element is individually mapped to the reference element, this is mapped to the reference element, this is mapped to the reference element, so on and so forth. While we do that, what we do is basically inside each of the physical elements you have got local degrees of freedom. So the degrees of freedom is nothing but the points where we measure or we assign the field quantities. So inside the physical element sigma 1 there are 2 points where we assign the field values. So those are exactly the end points of those elements. So we have the left point and then the right point. So similarly inside each of this physical element we have a left point and a right point. So these individual points are called as the local degrees of freedom. We call them local degrees of freedom because they are locally assigned to the physical element. Similarly, there is a global degrees of freedom which are represented by E0, E1, E2, E3 and E4. They are assigned directly to the number of nodes inside a domain. So the degrees of freedom has 2 different connotations. The first one, as I said, has to do with the basic domain itself. So that is the global degrees of freedom. So the global degrees of freedom is going to be equal to the number of nodes. If you are talking about a nodal element method, it is going to be the number of edges if it is going to be the edge element method. So let us focus now on the nodal element. So the number of nodes inside the domain is going to give me the global degrees of freedom. Similarly, the number of edges of an element. So if you are in a 1D, we have got only one choice where we have single line segments. If you are in a 2D, we have got multiple choice. We can have a triangle where we have inside each of the element 3 points which are represented by 3 areas. Let me explain this on the slide. So if you are in a 2D, you can have inside each of the element 3 nodes, or you can have a square where for each of the elements you will have 4 points, so on and so forth. So here the global will be dependent on total number of nodes, whereas the local will depend on your element shape. So if the element is a triangle, you have 3 degrees of freedom. If the element is square, you have 4 degrees of freedom locally inside each of the elements. So what we are going to do now is we are going to map the values that we have locally assigned to the global values, and this is the local degrees of freedom to global degrees of freedom mapping. So the first one has the left point and the right point. The second element, which is written as superscript inside the bracket, here 2. So these are the second elements, left and right. Third elements, left and right, so on and so forth. And then the global values are here, E0, E1, E2, E3 and E4. They are assigned to the node 0, 1, 2, 3 and 4. So let's go forward. So now we are going to say the value inside each of the node is going to depend on the value that I assign to each of the nodes, which is going to be the expansion coefficient Ej multiplied by certain basis function Bj. So inside each of the elements, this is like this. For the entire domain, it will be j equal to 0 to n. So I can split this into 2 things. One which contains all the bulk element, or which has all the elements plus the left hand side, and then the one which has the right hand side is separated here. So what I am going to do here is I am going to map to the degrees of freedom. So inside each of the element, I said there are 2 degrees of freedom in the one dimensional case. So we have the left hand side, we have the right hand side, we have the left hand side, we have the right hand side, so on and so forth. And we are going to collect all the terms that are assigned to a particular degree of freedom, global degree of freedom. So I can collect all the E0s in the equation, all E1s in the equation, all E2 in the equations, and then I can write them in this form. So the reason for doing that is I can map the elements such that I can write them in a matrix form later on. So this is the process which we have showed like before. You have all the elements plus the right hand side element, which is the boundary element. So with the local matrices at hand, we can construct the global matrix. So we have found inside each of the local matrix we have certain values, and we are going to substitute that values inside the global matrix. So the global matrix has a tridiagonal because there are going to be overlaps of the nodes. So what you are basically having is inside each of the element there is going to be contributions coming from a particular node. So let me explain this with a slide. So inside each of the element, let us say this is node 1, this is node 2, and I am going to compute the value of the fields at node 1 and node 2. And I said for simplicity case, let us say I have 2 basis functions that are defined. One is going from 0 to 1, the other one is going from 1 to 0, and let me write this one as the scale is, this is 1, this is 0. So when I am here in this particular point, the contribution because of this basis function is going to be the maximum, whereas the contribution because of this basis function is going to be the minimum. So inside an element we are always going to have a contribution from both the basis function that are defined on a particular finite element. So in this case, inside each of the finite element I have 2 linear basis functions that are defined, and those basis functions are going to impact the value. So I say here the field value is E1, here the field value is E2, and these are the expansion coefficients that I am going to use, and this is going to be my, so this is the one which is here is going to be my V1, and this is going to be my V2. So I said inside each of the element my value is going to be, E approximation is going to be E1 V1 plus E2 V2. So how do I know what is happening? What is happening here is there is a kind of a contribution that is going to come from this basis function and this basis function. So when I am at this point, at this particular node, the contribution of this basis function is going to be the maximum. When I am at this point, the contribution for this basis function is going to be maximum, and the other basis function is going to change accordingly. At inside each of the element, the sum of the basis functions contribution should always be equal to 1. So inside each element, so sum of Vi should be equal to 1. So what's happening here is I have a contribution of this node on this node itself, and I will have a contribution of this node's potential on this node, or in the case of the field what we are computing, the value of this field on this node, the value of this field on this node. Similarly, the value of this field on this node, the value of this field on this node. So totally inside each of the element you are going to have a 2 by 2 matrix. So you have a value that are represented by 2 by 2 matrix. The 2 by 2 matrix are made such that the contribution will be 1 comma 1, so the node 1 on 1, and this will be 2 comma 2, and this will be 1 comma 2, and this will be 2 comma 1. So that is what we are going to see when we are going to populate this particular matrix, and it is tri-diagonal because the reason is when I am in a domain which has totally 4, in this case we have 4 elements, so there are totally 5 points. So what I am going to have here is 1, 2, 3, 4, 5. So this is sigma 1, sigma 2, sigma 3, sigma 4, and in this point this node is the same node that is for both this element and this element. Similarly, this node is the same node for this element and this element. In other words, this node is overlapping both for this element and this element. That is what we are saying here, and since we have a 2 by 2 matrix and the nodes are overlapping on each other for each of the elements, we will have a tri-diagonal matrix. And now we are going to populate it. As I explained, the first combination is because of this element, which is the first element. This is the first node's contribution on the first node itself, the first node's contribution on the second node, and the contribution from the second node on the first node, and the second node on the second node itself. Similarly, when I go to the second element, there is an overlap. The overlap, as we can see, the second node of the first element and the first node of the second element, they are the same. So we are going to have an overlap. However, the subscripts are different because in this case it is belonging to the first element, in this case it belongs to the second element. Likewise, I will have the third element contribution and finally the fourth element's contribution. So with this we are going to now assemble in the same manner also the stiffness matrix. So what we have done now is for the material matrix, the stiffness matrix will also have the same form. But one thing is missing. What is missing is the value of G. Remember, we have given the value for G to the boundary conditions. If you go back to the slide where we have discussed about the value of different elements, what we see here is this component is going to be the contribution because of the boundary conditions, and that is what we are going to do in this particular matrix, and it is going to be slightly different, whereas in a sense it is going to be easy and straightforward. Let us say we are assigning certain PEC condition, and the condition is we have the value of E of x naught and E of xn is equal to certain constant. If it is a perfect electric conductor, the tangential components will have 0. If it is a not perfect conductor, if it is a jump condition, you will have certain values. Okay, let us assume that it is going to be certain value C, and we are now going to substitute this inside this matrix. So we know the value of E of naught and E of n equal to 4 will be equal to C. So that is what we are doing now here. We have substituted the value on the right hand side as C, and similarly we have changed the values of E naught and E4, because this matrix will give the value of E. When you multiply the first row, you will get E naught equal to C. Similarly, the last matrix will give you E4 equal to C, and this value and this value should be logically 0. This is also coming from the boundary condition itself. But assume that this second entry n element is A, first element of the second row is A, and the last element of the fourth row is B. So we can manipulate this particular matrix in such a way that we can eliminate E naught and E4 because their values are given, they are fixed Dirichlet boundary condition. So we can only have a matrix linear algebraic form for E1, E2 and E3 whose values are unknown. So that is exactly what we are going to do now. So we are going to do the matrix manipulation where the value here A and B are coming from the previous slide, where these are nothing but the first entry in the second row, the last entry in the fourth row, and we are doing the matrix manipulation. By doing that, what we have done essentially is we have reduced the matrix from a asymmetric matrix to a symmetric matrix again, and we have also reduced the number of unknowns from 5 to 3. This will have a significant improvement in the case of a large scale problem in 2D or 3D, where we have to only focus on, let us say, n number of elements versus n plus x number of elements. So this is going to help you in faster computation and also reducing some of the unknowns to certain boundary conditions will help you to cleverly model the problem in such a way that you can get with the least number of calculation the right answer or the approximate answer. So now we have looked into a very simple case for the basis function. In the one dimensional case, as I have explained here, what you see here is a linear interpolating function whose values, or in other words whose degrees of freedom inside the element are in 2 points. Assume that I have more than 2 degrees of freedom inside each of the element. What do I mean by that? For example, so assume that instead of having 2 degrees, we have 3 points inside each of the element. So the local degree of freedom is so what we are going to do now is how can we model such problems. So that is what we are seeing here. So we can do, instead of a linear interpolation, we can use a quadratic interpolation, where instead of 2 nodes we will have 3 nodes. So as you see inside each of the elements we have the left point, the right point and also the middle point, and likewise the numerical manipulation is quite straightforward. So we will have the value going from 0 to 1 and also there is a point in between. So we can think about various interpolation functions or various basis functions. One option is to go for a kind of a quadratic function whose value is going from 1 to 0 and is quadratically changing, or you can have a kind of a sinc function whose value is having maximum at the middle and it's reducing on both sides to 0, and it can also have the linear interpolation which I discussed in this earlier case. So regardless of what you do, the sum of the basis functions inside each of the element should be always equal to 1 at each of the points. So if I am in this point, the sum of the elements, the contribution from this element, the contribution from this element should add up to 1. Similarly, the contribution from this element, the contribution to this element should add up to 1, so on and so forth. So with that being said, we have come to a stop. What we will do now is we will look into a problem that's very common in electromagnetics, which is Poisson equation. So now we have dealt with mostly one dimensional problem. What I would like to do is I would like to do it in 2D, show you the logic behind it on paper, and also do it on a MATLAB program to get a sense of what the solution will look like, how the MATLAB can be used for solving such problems. We will do that while we come into the next module. Thank you.